You know, what do the orbit of Mars, the design of a modern stadium, and a whispering gallery all have in common? Well, they're all defined by one single elegant shape, the ellipse. Today we're going to demystify this fundamental curve, and trust me, you don't need to be a math genius to see just how beautiful its design really is.
All right, so first things first, what actually makes an ellipse an ellipse? It all comes down to one surprisingly simple, totally unbreakable rule that governs its perfect form.
Okay, that definition sounds a little dense, right? But what it means in practice is actually way simpler than it sounds. Just imagine you have two pins stuck in a board. Those are our foci. Now take a loop of string and throw it around them. If you pull that string tight with a pencil and trace a path all the way around, you get a perfect ellipse. The real secret sauce here is that the total length of that string never, ever changes.
And this diagram here shows that rule perfectly. See that point P1? The distance from it to the focus S plus its distance to the other focus S' adds up to one specific length. Now here's the cool part. Pick any other point, P2, P3, doesn't matter where. The sum of their distances to those two foci will be exactly the same. That constant sum is the magic trick that defines the entire shape. Okay, so now that we've got that fundamental rule locked in, we can start to break the ellipse down into its key parts. Let's take a look at its anatomy.
This diagram is going to be our roadmap for the next few minutes. It lays out all the lingo we need to really speak the language of the ellipse. So let's break it down, piece by piece.
First up, we've got the center. Super straightforward, right? It's the geometric heart of the ellipse, the dead middle, the point of perfect symmetry. Pretty much everything else is measured from this one spot.
Next is the major axis. Think of this as the ellipse's spine. It's the longest possible line you can draw straight through it, cutting it in half the long way. It runs right through the center and connects the two widest points. And that distance from the center to one of the ends, we call that A, which makes the whole length 2A.
And if you've got a long way across, you've got to have a short way, right? That's the minor axis. It's perpendicular to the major one, connecting the narrowest points, and it also runs right through the center. The distance from the center out along this axis is called B. So the total length is 2B.
So what about the 2 points at the very ends of that long major axis? Well, they get a special name, the vertices. They're simply the 2 points on the ellipse that are the absolute farthest apart from each other.
And that brings us right back to the foci. It's so important to remember, these aren't just random dots. They're the two secret ingredients, the anchor points that dictate the whole shape. And as you can see, they always sit somewhere along that long major axis.
So we've got the concept and we've got the anatomy, but how do we bottle all of this up into a single, elegant equation? Let's translate this shape into the language of math.
And there it is, the standard equation for an ellipse that's centered at the origin. I mean, it looks almost too simple, doesn't it? But that's the beauty of it. All those properties we just talked about are packed right into this one neat little formula.
And here's the best part. Those letters, A and B, in the equation, they aren't just some random math variables. They are the exact measurements we just identified. A is half the major axis, and B is half the minor axis. The equation is literally built from the physical size of the ellipse itself.
Okay, but wait a minute. What if our ellipse is, standing up instead of lying down? The equation has a really slick way to tell us which is which. Let's look at the two orientations. I mean, visually, the difference is obvious. One's wide like a football, the other's tall like an egg. The really amazing part is how just one tiny change in the equation accounts for this difference and shifts everything from the shape to where the foci are located.
And the difference is actually really simple. For a horizontal ellipse, that semi-major axis A is longer than B. It's wider than it is tall, and the foci sit on the horizontal x-axis. But for a vertical ellipse, B is the bigger number, so it's taller than it is wide, and the foci flip up to the vertical y-axis. It really is all about which axis is the dominant one.
So you want a super simple shortcut? Just look at the equation. Find the bigger number on the bottom. Is it under the x squared? Boom, it's a horizontal ellipse. Is the bigger number under the y squared? Then it's vertical. Seriously, it's that easy.
Okay, let's bring it all home. We're going to circle back to those foci one last time because we're about to connect everything we've learned and reveal a fundamental property that just ties it all together.
This right here, this is the heart of the ellipse.
Remember that constant sum from our string and pinch trick at the beginning? Well, it turns out that constant isn't just some random value. It has a very, very specific meaning. And get this, that constant value is precisely 2a, the total length of the major axis. So that loop of string we imagined, its length is exactly the same as the ellipse's longest diameter. It's just a beautifully complete idea where everything clicks perfectly into place.
There's one last piece of vocabulary that's really helpful, and it's called eccentricity. Just think of it as a number that tells you how stretched out or squashed an ellipse is. It's a single number, e, that goes from 0 up to 1. An eccentricity of 0, that's a perfect circle. And as e gets closer and closer to 1, the ellipse gets more and more elongated.
So we've dissected the anatomy, we've looked at the math, but you might be thinking, so what? Why does any of this matter outside of a textbook? Well, it matters because this shape is literally written into the fabric of our universe.
This isn't just a formula, it's a fundamental blueprint of nature. It was a huge deal when Johannes Kepler figured out the planets don't orbit in circles, but in ellipses, with the sun sitting right at one of those foci. Architects have used elliptical arches for centuries to build incredibly strong and beautiful structures. The properties we've explored are all around us, shaping both the natural world and the one we've built. So the only real question left is, now that you know its secrets, where are you going to spot the ellipse next?